This is the Chem 1 lecture over VSEPR and determining the polarity of molecules. So yesterday we looked at Lewis structures, and as you look at these Lewis structures of these various covalent compounds, you see that they're very, very two-dimensional. They're all drawn flat on a piece of paper, but as we know, especially with our Bohr atom of the model, we don't live in a two-dimensional world. Molecules are really three-dimensional. This is why we came up with the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. And what that states is because electrons are negatively charged, they are going to do whatever they can to get as far apart as possible. So if you look at a substance in two-dimensional space, the furthest apart you could draw this substance is 90-degree angles. Right there, right? If we had 4 atoms bonded to our central atom, the furthest apart you can make those ions is 90 degrees. But in 3 dimensions, it's almost impossible to draw this. I'll show you guys my little picture. But one's going like back into the board and one's popping out of the board. You can actually make these angles greater than 90. And so that's what they're going to do. They're going to form these 3-dimensional shapes that have angles greater than 90. So how do you use VSEPR theory? First thing you're going to do is draw that Lewis dot structure for the molecule. So basically step 1, just like your homework last night, you're going to nasal. Then you're going to count the number of links on the central atom. Remember, a single bond is a link, but a double bond counts as only 1 link, and a triple bond also counts as only 1 link. So basically you're saying how many things are attached to it. So not how many lines are there, but how many things are attached to it. So something like this has 1 thing attached. And then determine the number of lone pairs. And all of these are only talking about whatever atom's in the middle. We're going to determine shape from our central atom. So you guys have this handy-dandy chart where if there are 2 links on the central atom and no lone pairs, it's linear. 3 links, no lone pairs, it's something called trigonal planar. 2 links, 1 lone pair, it's bent. 2 links, 2 lone pairs, it's bent. 4 links, no lone pairs, it's tetrahedral. 3 links, 1 lone pair, it's trigonal pyramidal. Now there's more than these lists, but this is the ones I'm going to expect you to know. And you'll be able to see a lot when you start drawing them. And we're going to build them in 3-dimensional space on Thursday as well. Here's another way to look at it. This is the number of lone pairs. So 2 lone pairs, 1 lone pair, 0 lone pairs, 1 lone pair, 2 lone pairs. And then this is the number of links. So 2 things linked, 3 things linked, 4 things linked. So if it's got 2 things linked and no lone pairs, it's linear. If it's got 3 things linked with no lone pairs, it's trigonal planar. 3 things linked, 1 lone pair, it's bent. 4 things linked, no lone pairs, it's tetrahedral. 4 things linked, 1 lone pair, it's trigonal pyramidal. 4 things linked, 2 lone pairs, it's bent or angular. In this case, they're counting electrons as links. Either way you look at this, you're going to get the same shape. And it's a lot easier when we just do some examples. So let's move forward and do that. CO2, draw the Lewis structure. So if I was to nasal this, NaSl, carbon needs 8, oxygen needs 8. I have 3 atoms that all need 8, so 3 times 8 is 24. Carbon has 4 available, oxygen has 6, and there's 2 of them. So that's 12 plus 4 is 16. 24 minus 16 is 8, which means 4 bonds. 16 minus 8 is 8, which means 4 lone pairs. So when I draw this, I end up with carbon in the center. I need 4 bonds, but I only have 2 atoms, so I'm going to put double bonds between them both. And then carbon now has 8. Oxygen has 8. When I draw, it's 4 lone pairs, and the other oxygen has 8. How many links are on that central atom? How many things are attached to it? There are 2 things attached to it, this oxygen and this oxygen. Remember, double bonds still count as 1 link. How many lone pairs are on this carbon? 0. What shape is this called? The answer is linear, and it looks linear, right? It looks like a straight line. Let's do another one. BH3. We got boron in this one. What do you know about boron? He's a moron. So as we nasal this guy, NaSl, boron needs 6, and then we have 3 hydrogens that need 2. That comes out to 12. Boron has 3 available. Hydrogen has 1 available, so that's 6. Needed minus available is going to come out to be 6, so that's 3 bonds. And available minus shared will come out to be 0. So I got 0 lone pairs. So when I draw this, boron's in the middle, and I have those 3 hydrogens. Notice there's no lone pairs anywhere on this atom, right? So if this is my central atom, how many things are linked to it? 1, 2, 3 links. How many lone pairs? 0. This is a shape called trigonal planar. Trigonal, guys, what does tri mean? It means 3 links. Planar means it's going to lay flat because it doesn't have those lone pair electrons. So I'm just basically going through and showing you an example of each shape. Here's NO2 with a -1 charge. Remember, in chemistry, if there's no negative or no number, it's always assumed to be a 1. So we can NaSL this guy, NaSL. Needed, I have 3 atoms all needing 8, so that comes out to 24. Available, nitrogen has 5 available, plus 2 oxygens that each have 6 available, plus this -1 right here means I've gained an electron. So I'm going to add 1 into my available. So 6 times 3 is 18. N minus A, 24 minus 18 is 6, so that gives me 3 pairs. A minus S, 18 minus 6 is 12, so that gives me 6 lone pairs. So when I draw this, that nitrogen goes in the center. I need 3 bonds. It doesn't matter which one my double bond goes to. And then when I draw on those lone pairs, this oxygen with a double bond is going to need 2 more pairs, 4 more electrons. The oxygen with a single bond is going to need 6 more electrons, so 3 more pairs. And my nitrogen's going to need 1 more. And of course, I'm going to put those brackets. I got that -1 right there. How many links on that central atom? 2. How many lone pairs on the central atom? There's 1. This shape is called bent. And it looks bent, right? So how this compares to linear is linear doesn't have any lone pairs. As soon as you add those lone pairs, these are electrons, so it's going to literally push them down. That lone pair is going to repel those electrons that are in that bond, which gives it that bent formation. Here's water, H2O. Let's look at its structure. Let's NaSL it really fast. NaSL. I got 1 oxygen that needs 8 plus 2 hydrogens that each need 2. That's 12. 1 oxygen that needs 6 plus 2 hydrogens that each have 1. That's 2, so that comes out to 8. N minus A is 4, so that's 2 bonds. A minus S is 4, so that's 2 lone pairs. So I'm going to put that oxygen in the middle, not the hydrogen. I'm going to do my 2 bonds and my 2 lone pairs. So I have 2 links, 1, 2 on my central atom, and 2 lone pairs. This does the exact same thing the last one did. It's also called bent. Those lone pairs in this case push it down. So before, my linear, it pushed it down when I added that lone pair. And now I have 2 lone pairs. It's going to even push it further down. So this is like a 180-degree angle. This is something less than 180, and this is even less than that one. So this is less than 180, and this is even less than 180 because those electrons are pushing really, really hard. 2 more shapes to go. We're going to make it CCl4. This is carbon tetrachloride. We've NaSL'd this one before. We did it in our yesterday's lecture. I know I'm NaSLing these really fast. If you need to go back and watch the video again. I have 5 things that all need 8. That's 40. Available. Carbon has 4 plus 4 chlorines that each have 7. That's 32. So N minus A is 8. So that's 4 bonds. And then A minus S comes out to 24. So that's 12. I can draw 12 lone pairs. So it's going to look something like this. Oh my goodness. This is carbon tetrafluoride. These should be CLs, not S. Sorry, y'all. I don't know how that mistake got made, but same difference. Yeah, I'll draw it off to the side. Cl bonded to C, bonded to Cl. Like I said, we did this one the other day. Good. How many links do we have on that central atom? Well, we have 1 chlorine, 2 chlorine, 3 chlorine, 4 chlorines. How many lone pairs? 0. This is a shape called tetrahedral. You have trouble remembering this. Remember that tri means 3? Tetra means 4. Have anyone here ever heard of the game Tetris? The game Tetris is called that because every shape is made of 4 blocks. So you have the square that's made of 4 blocks, you have the tall skinny one that's made of 4 blocks, you have the zigzaggy one that's also made of 4 blocks, you got this guy made of 4 blocks. I'm sure oh, and then this was one, of course. How could I forget? That's why this game is called Tetris, because they're all made of 4 blocks, and that's what tetra means, it's 4. So if it has 4 links, no lone pairs, it is tetrahedral. And our last shape, NH3, we also NASL'd this one yesterday. So needed, nitrogen needs 8. You have 3 hydrogens that each need 2. That comes out to 14. Nitrogen has 5. You have 3 hydrogens that each have 1. That comes out to 8. Needed minus available, 14 minus 8 is 6, so that's going to be 3 bonds. Available minus shared is going to be 2, so that's 1 lone pair. So when I draw this, I'm going to have those 3 links. Those 3 hydrogens are linked to my central atom. And then I have that 1 lone pair. This one is called trigonal bipyramidal. Again, if it has 3 links, you're going to see that begins with trigonal, but this one's called pyramidal. Now the other one laid flat. You guys remember when we had 3 things attached, but no lone pairs, it lays flat, called planar, like flat on a plane. When you add that lone pair onto that X, it literally pushes those 3 bonds down, and it makes like a pyramid shape. I'm not very good at drawing pyramids, but there's my X, and there's that lone pair. It makes like a pyramid shape. So what that lone pair does is it pushes those 3 bonds down, so it looks like a pyramid, hence trigonal pyramidal. So there are all those shapes. There's a picture of them again. Linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and bent as well. You guys have this chart, and when I come back, we will review this. Okay? So for now, all you need to do is be able to count the links and count the lone pairs to determine the shape. Polar versus nonpolar molecules. Now before we do this, let me preface with saying that before this moment, we talked about polar and nonpolar covalent bonds. When I'm talking about a covalent bond, I am talking about the electrons being shared between 2 elements. So here are my electrons being shared. Are they shared equally or unequally? So do these 2 electrons go like this, where they spend exactly as much time around each of those atoms, or are they shared unequally and they go like this? Oh, around the Y. Oh, around the Y. So this would be polar, nonpolar, where they're shared equally, and this would be polar. What I'm talking about here is entire molecules. So just because something is made of polar bonds doesn't mean it's going to be a polar molecule. Or just because something's made of nonpolar bonds doesn't mean it's going to be a nonpolar molecule. So we use the word polar and nonpolar to describe both bonds and molecules. You determine if a bond is polar or nonpolar by their difference in electronegativity. For molecules, we're going to use some other sets of rules. So polar and nonpolar molecules is a polar molecule if all the electrons in the entire molecule are evenly distributed. Therefore, there's no side that has more electrons than the other side. Basically, you're looking for symmetry with this guy. That's another big one. If there's symmetry, if you can cut it in half and it's the same on both sides, then the electrons are going to be evenly distributed. Nonpolar is when the electrons are not evenly distributed. Now, let me give you an example real quick of polar, like carbon dioxide. Do y'all see that this has that line of symmetry where you could fold it on itself? There's the same number of electrons on both sides. So this is a nonpolar molecule. Whereas something that's polar would be something like water. Do you see how all the electrons are on this side and there's none on this side down here? That gives this side a kind of a negative charge and this side kind of a positive side. This would be a polar molecule. Now there's a saying in chemistry that helps us understand why some things will dissolve in certain substances. And that saying is like dissolves like. So what this is telling you is if you have a polar substance, it will dissolve a polar substance. And if you have a nonpolar substance, it will dissolve nonpolar substances. Here's a little video that I found. It's not the best, but I have a good demo for you when I come back tomorrow. So here's a video showing you that correlation.
Nonpolar carbon tetrachloride is poured into a test tube. When the nonpolar colored solid is added, the solid dissolves in the carbon tetrachloride. When polar water is added to the test tube, it forms a layer on top of the carbon tetrachloride, since water is immiscible with and less dense than carbon tetrachloride. When nonpolar hexane is added to the test tube, it forms a layer on top of the water, since hexane is immiscible with and less dense than water. When the test tube is vigorously shaken, the two nonpolar liquids form a single layer at the bottom of the test tube, and the polar water layer sits above this layer.
So you can see that because one is polar, let me close this out. Because one is polar, it dissolved the polar substance, and if one was nonpolar, it dissolved the nonpolar substance. Here's a little video, or not video, a comic. It says, "Help, help, I'm dissolving." And the bear on the iceberg says, "The bears aren't soluble." And he said, "That's easy for you to say, you're not polar." With a polar bear dissolving in polar water. Thanks, Connor Parent, for sending that to me. So how do we know if something's polar or nonpolar molecule? Remember, to find if a bond is polar or nonpolar, we look at the difference in electronegativity. But if it is a molecule, we're going to look at that central atom again. And if it has no lone pairs attached to it, and every atom attached to it is the same atom, it doesn't necessarily need to have the same number of bonds, but the same atom, so they're all oxygens or they're all carbons, it's going to be nonpolar. If it has no lone pairs, but everything attached to it is not the same, therefore you don't have that symmetry, you will be polar. And if it has lone pairs on that central atom, it's automatically polar. Now, remember, there's some that we know have lone pairs. Anything that comes out bent, trigonal, pyramidal, these always have lone pairs. So these will always be polar. Just a little helpful hint for you. They always have lone pairs. So if you say something's bent or trigonal pyramidal, you know it's polar. But besides that, you need to use these rules. First, look for lone pairs. If there are some, boom, polar. If there aren't, is everything attached the same? If so, it's going to have that symmetry and be nonpolar. But if everything attached is not the same, it's going to be polar. And here's a little flow chart that gives you the same thing. Are there lone pairs? Yes, polar. If no, you come down here. Is everything attached to the same type of atom? Yes, nonpolar. No, polar. So an atom can only be, or excuse me, a molecule can only be nonpolar if it has no lone pairs and everything attached is the same. So let's do a couple examples. NH3, we've NASL'd this one before. Once again, 8 plus 3 times 2 comes out to 14. 5 plus 3 times 1 comes out to 8. N minus A, this is 6, so 3 bonds. A minus S is 2, so 1 lone pair. So I have N bonded to 3 hydrogens. I've got to have 1 lone pair. So its shape, this is exactly what you're going to do on your homework, will be trigonal. It's got 3 things attached. But because it has this lone pair, it's going to push those 3 things down, make it look like a pyramid. Trigonal, pyramidal. Is it polar or nonpolar? Let's look at our central atom, which is our nitrogen. Does it have lone pairs? The answer is yes, it does. So it is automatically polar. So you'll have to do all of these steps on your homework. You're going to NASL and draw it just like you did on last night's homework. But then you're just going to add that last step of telling me its shape and whether it's polar or nonpolar. Carbon tetrachloride. We've done this one before too. We got 5 that all want 8. Comes out to 40. Carbon wants 4 plus 4 chlorines that have 7. That comes out to 32. N minus A is 8. That's 4 bonds. A minus S, 32 minus 8 is 24. That's 12 lone pairs. Carbon in the middle, our chlorines all around. 4 bonds. 12 lone pairs. Shape. I got 4 things attached to the central atom. All 4 of those chlorines. 4 things. What is that other word for 4? It does this all the time. Sorry, my smartboard stopped working, but it is still recording. I just wanted to check to see if it was. All right, I think we're back. What's that other word for 4? Tetra, as in Tetris. So this is tetrahedral. Let's talk about polar and nonpolar. Looking at our central atom, there are no lone pairs. So the next thing we have to ask ourselves, is everything attached the same? Yes, they are all chlorine. If that's the case, there's some symmetrical. There's some symmetry here, right? I could cut this in half and fold it. It's going to be identical to itself. So this is a nonpolar molecule. So your homework is going to be the entire back of that sheet. I will be checking that in your homework that was due today. Tomorrow, I'll show you that like dissolves like demo. And then we're going to do a lab where you're going to actually get to see these shapes in 3 dimensions. Good luck.